Greetings. Today, our Group 7 will present our project titled The Effect of Bridge Design on Weight Bearing Capacity. Introducing our team members, my team leader which is Muhammad Qasim, my other team members Muhammad Ali Burhan, and of course myself Muhammad Syamia Kimi. Here is an overview of today's presentation. We will start with the introductions and objectives of the project, followed by the description of the bridge testing system. Next, we will discuss the response variable, factors and levels, and the experimental design used in this study. Finally, we will present the results, discuss the statistical and engineering analysis, and conclude with the key findings and the best bridge configurations. And we will also show our experiment demo video in our presentations. So, bridges are an essential part of modern infrastructure because they help reduce travel time, transportation costs, and fuel consumption. To ensure that bridges are safe and reliable, engineers must understand how different materials and structural designs affect their strengths. In this project, we built and tested 4 model bridges using different materials and designs. By applying loads anti-failure, we can compare their performance and determine which combination provides the highest weight-bearing capacity. Statistical analysis is then used to evaluate the results and identify the most effective design. The main objective of this experiment is to evaluate and compare the braking load of 4 different bridge models. 2 factors were investigated. The first factor is material type, which consists of plastic straws and popsicle sticks. The second factor is bridge design, which consists of a flat beam design and a Warren truss design. To ensure a fair comparison, all bridges were constructed with the same dimensions of 13 cm height by 30 cm length by 9 cm width and use the same joint type, which is hot glue. The load was then increased gradually until the bridge failed. This experiment is conducted and shared among the super team. This experiment uses a structural evaluation system that consists of 3 subsystems. First is the structural test subsystem, which evaluates the maximum load capacity of bridges made from different materials and designs. Second is the mechanical loading subsystem, where weights are added gradually at the center of the bridge. This creates a controlled downward force that allows us to determine the failure point accurately. Third is the data acquisition subsystem, which records the failure load and analyzes the results using a 2 to the power of 2 factorial designs. This statistical method helps us compare the effects of material type and bridge design on structural performance. The response variable in this experiment is the ultimate structural load capacity, measured in newtons. This refers to the maximum load that a bridge can withstand before it collapses. To measure this value, weights are added one by one at the center of the bridge until structural failure occurs. The maximum load recorded before collapse represents the bridge's weight-bearing capacity. That's all for my part, and for the next part, I'll pass on to my other team members, which is Muhammad Ali Burhan. Thank you.
Okay, now let's look at the factors and level defining our experiment. We evaluated bridge performance by manipulating 2 primary factors while keeping our other variables completely constant. For our manipulated variables, the first factor is material, where the plastic straw represent our low level and popsicle sticks represent our high level. The second factor is design, with a flat beam deck as our low level and a Warren truss as our high level. To ensure a fair test, we maintain strict constant variable across all configuration. Every bridge shares the same exact dimension of 13 by 30 by 9 centimeters. The load was added at the same rate increment, and we use hot glue gun as a consistent adhesive for all joints. Then, to systematically analyze this variable, we implement a 2-square full factor experimental design. These metrics allow us to study both individual and combined effect of our material type and bridge design on total load capacity. Because we have 2 level and two factor tested over a single trial. Our total setup required exactly 4 distinct experimental runs, as you can see in this design matrix. Run 1 serve as our absolute baseline using low-level plastic straw and a flat deck. Run 2 introduced the high-level Warren Truss design to the plastic straw. And Run 3 tested our high-level popsicle sticks material on a flat deck. And finally, Run 4 combined both high-level variable popsicle sticks with a Warren Truss design while keeping our hot glue joint and structural dimension entirely constant throughout. And before we move on to the result, we will show you the demo and testing of a bridge. Moving on to the raw result of our 4 experimental runs based on our testing and demo of the bridge. As we can see, a clear trend in how material and design impacted our maximum load capacity. Looking at our lower level combination, the baseline plastic straw flat deck in Run 1 failed at just 10 newtons of force. When we upgraded the geometry to Warren Truss in Run 2, the capacity tripled to 30 newtons. Notably, keeping a flat deck but switching a high-level popsicle stacks in Run 3 only yield 15 newtons of capacity. However, the real breakthrough happens in Run 4. When we combine both high-level factors, the solid popsicle sticks material pair with geometric advantage of the Warren Truss, the maximum load capacity skyrocketed to 145 newtons.
Assalamualaikum warahmatullahi wabarakatuh. In this part, I will talk about statistical main effect and calculation of percentage difference, along with graphical representation and engineering errors and conclusion. So for the first one, the main effect of material is 60 Newton. This shows that wooden popsicle stick is much stronger compared to the plastic straw. Second, the comparison of design and geometry. The Warren Truss has a main effect of positive 75 Newton over the flat beam deck, and this is much higher and plays even larger role compared to the material itself. Next, when calculating the percentage difference, When comparing with highest level material, which is hold around 145 Newton, with lowest level configuration, which is hold around 10 Newton, it shows the impressive amount of 1,350 percentage difference of total load capacity. This shows that it's much stronger, and this shows the popsicle stick with Warren truss is much stronger compared to all of the bridge that we compared and tested in this experiment. Next, moving on to graphical analysis and engineering analysis of the failure modes. The flow of flat beam deck. The flat beam deck has no truss to support its load, and since there is no webbing, the boat bridge hold only with the least amount of load, which is around 10 to 20 Newton. So next, when talking about the impact of Warren truss geometry, the plastic straw with Warren truss geometry successfully hold around 30 Newton as a peak load capacity. It is more high compared to the boat bridge that we compared before. And when we optimize it with the higher level material, which is popsicle stick with Warren truss, it achieved the impressive amount of peak load of 145 Newton. This shows that plastic wood, solid wood fiber completely surpass localized buckling and convert the pure axial tension and compression until it reach peak capacity, breaking capacity of 150 Newton. To conclude that, our testing proved that maximizing the structural integrity relies on three important factors. Important setting, which is popsicle stick as a material, and pairing with Warren truss design, and with the constant hot glue gun for all the bridge that we tested. Switching from weak to plastic straw, from weak plastic straw to popsicle stick, it completely eliminates localizing, buckling, and managed to and providing a structural material stiffness, and this perfectly redirect the downward and force into pure axial tension and compression between the truss geometry itself. And finally, the popsicle stick with Warren truss hold around 145 Newton. This means that truss geometry and material are relies on each other, and which in statistical term is codependent. So to maximize structural safety, geometry of truss, geometry and material plays an important role and important for each other. That's all from us. Thank you.